Okay, friends, we're going to start a new chapter today. It's called Related Rates, which builds upon derivatives, which built upon limits. So your knowledge of derivatives is going to be really helpful in derivatives. And we're also going to be applying those derivatives to situations that we can all relate to. So let's start. So this related rates split into two different halves. We're going to be looking at velocity and acceleration, and then we spend the end of the chapter looking at related rates themselves. So here we go. So you'll notice that right off the bat, we're going to assign 7 go forward questions. So get on that right away. The notes are really good to support you in your understanding, and we're going to get right into velocity right now. So obviously, velocity and acceleration are things we all experience if we've ever been in a car or on a bicycle or have moved from a standing position. So velocity is all around us, makes life fun, makes life interesting, and can obviously be dangerous in certain situations. So we're going to keep things safe. We're going to keep things grounded in our mathematics right now. So let's get in. So today, here's the content outcome. Can show that how derivatives are related to distance, velocity, and acceleration, algebraically and graphically. And the content outcome is also can solve problems involving distance, velocity, and acceleration. But today we're going to focus on the bolded stuff, which has to do with velocity. Today should be a day where you should be able to make connections between the mathematics that we're doing and clear examples we see outside and all around us. And also you're going to be using the vocabulary, and I want you to be using the vocabulary interchangeably between velocity, acceleration, and their related and correlated derivative language. Okay? So I thought I'd just show you this cute little clip just to start off. This is the world record for the blob jump, and you can see that this person is being thrust into the ground. And I'm curious, as you watch this guy fly, can you tell when the velocity is changing? Is there ever a time where it's super easy to say what the velocity is? For example, when the guy's sitting on that blob thing, obviously there's no velocity. And when he's in the water, the velocity is limited. There's also another time where velocity is 0, and we're going to speed up and see if you can find it. So why don't you tap on the screen when the velocity is at 0? And right at that moment there, the velocity is 0, isn't it? Because we're shifting from moving up to moving down, and that's a clear spot where velocity is 0. So we're just going to be thinking about velocity in a variety of ways. And that was a world record in 2000 something. I can't remember when it was. Okay, so this is where we're going today. How long does it take for an object to hit the ground? How long does it take for an object to reach its maximum height, and determine the total distance of an object traveled? Once again, you're going to be connecting these math concepts to each other within the math context. So you're going to be connecting this chapter with prior chapters, and also this chapter with the world around you that you see. And you're also going to be playing around with some new vocabulary. So let's get it down. Okay, so just as an introduction, okay, so what does velocity mean? So some of you will have some experience with this, and some of you won't. But the way you could walk through this is you could ask the question and see if you know the answer, and just walk through this verbally. But what does velocity mean? Well, it's the change in distance with respect to time. It's calculated by dividing the distance by the time that has elapsed. So when you get in the car and you start moving, your distance is changing, and depending on how long it takes you to get there would be one way of determining the speed. Now, we know that with driving in a car, the velocity is often changing. So there we go. So the following formula determines how far the object travels in a given time. What does dh dt mean, or what does h prime mean in this context? Okay, so the h here is referring to a height of some kind, and the t refers to time. So this is really, if we found dh dt, or the derivative of this thing, we'd be trying to determine how is the height changing as time changes, which is essentially speed or velocity. Okay, so here's another question. A ball is thrown into the air. What will the height be at the exact moment the ball hits the ground? Please do not overthink this. When the ball hits the ground, the height would be 0 because it is on the ground. So I want you to be, I'm priming you for some questions later that may come along where you might overthink it. So don't overthink it. Visualize what we're talking about, draw pictures, estimate situations so that you can visualize it, that you can picture it, take the ideas from your head and put them onto the whiteboard or a piece of paper. And that'll make making sense of this more constructive. Okay, a ball is thrown into the air. What will the velocity of the ball be at the exact moment it reaches its maximum height? So, maybe drawing a picture here might be helpful. So if we go, it's thrown up and it comes back down, and they're wondering, what's the velocity right there? Hopefully when you see this picture, you're like, wow, okay, that makes sense to me. It had a speed to get us to that point, but at a certain point it starts slowing down, and actually it flattens out at 0 for an instant there before it comes back down. A frog jumps up to a maximum height. So this is my frog that I'm going to draw with some big eyes here. It's going to go up, and then it's going to come back down. Okay, and it says determine the total vertical distance that the frog travels. And it goes 1.12 this way and 1.2 this way. And so we would see that the total distance would be 2.4. Many people might be tempted to think it's 1.2. Some people might even say it's 0 because he went up, he came down, and he's in the same spot. But if we draw the picture, we know that he went one way and came back down, so it has to be 2.4. Okay, here's a situation that you might find yourself. You're at the top of a cliff with a lolly. Unfortunately, it falls from your hand. The lolly is dropped from a cliff that is 122.5 high. Its height in meters after t seconds is given by this little equation right here until it hits the ground. Draw a picture to model this unfortunate situation. Do not erase your picture. You will need it for the next question. So I don't know. Now let's draw this picture. So here's a cliff. Here's the lolly. Let's get the height, 122.5, and maybe we put that demarcation there, or maybe we say that this height here to here is 122.5, and so it's being chucked down now. Of course, from a graphing standpoint, it would look like it's falling straight down, but as time goes, it would look more like that. Okay, so I hope you appreciate that. It depends what this horizontal axis is. If it's a horizontal distance, well, it would be just straight down. But if it's time, and that's what this equation is, it wouldn't be going straight down. It would be going more out, like so. So what I want to do is just show you that's what it would look like. That's what it could look like. And that poor lolly smashed into the ground there. It fell from this cliff, and it did go straight down if we're talking about a horizontal distance here and a vertical distance here. But if we look at it in terms of time, and this is that exact equation there, we can see that as time progresses, this lolly is kind of would look more like that. Okay, and we can see, if you think about the velocity here, the velocity is actually increasing as we go down, because initially it's going to pick up speed as it goes. So hopefully you can picture that, you can visualize that, you can explain that. Okay, so hopefully I can clear all this stuff out. Okay, so we've looked at this guy right here. A lolly is dropped off a cliff that is its height in meters. Oh, did we already do that? Oh, sorry. Okay, let me just erase this. I lost some of my erasing feature here. Oh, clear screen, that's what I was looking for. How far has it fallen after 2 seconds? Okay, so it depends how you want to do this. If you remember, if we have our graph like this and it's going like this, after 2 seconds, remember we could do it like this. We could go 1 minus 4.9 and then put the little 2 in there. Now what that will give us, it won't give us 19.6. What it's going to give us is the height. Okay, so when I calculate that, it would be 122.5 minus 4.9 times 2 squared. And so it would be, its height would be 102.9. And so what we want to do is subtract that from 122.5. And we are going to get 19.6. Another way you could look at that is you could just use this piece right here, and negative 4.9 times 2 squared is 19.6. So some of you will have picked up on that. Okay, so don't confuse here. What this equation here is telling us what the height is, and this says how far has it traveled after 2 seconds. How far above the ground is it after 3 seconds? So again, we're going to sneak and put the 3 in right there. And think about it this time. Do we need to subtract anything? Like would this give us the answer here? Or do we need to calculate the whole thing? And of course, this question is the whole thing because it says how far above the ground is it? So it's asking how high is it in relation to the ground? Okay, so that's where the 78.4 is. And how far above the ground is the object after 6 seconds? So what we're going to do, once again, is we're going to put that 6 in right there. And when we calculate it, we end up getting a negative number, which we should interpret as not making sense, which means that it's underground is what it would mean. It's not actually 53 meters under the ground. It just means that our question didn't make sense, that lolly is not burning a hole through the ground there. Okay, so those are some sort of some warm-up questions. Let's see, a lolly is dropped from a cliff that is 122.5. Its height in meters after t seconds is this until it hits the ground. Find the velocity. Okay, so now we're talking velocity. So what we want to do is find the derivative of this. So the velocity is going to equal dh dt, or the first derivative. And so it would be important that you'd be able to use that terminology there. So if we calculated this, what I like about this chapter is the derivatives are, after that first chapter we did, are really so straightforward in comparison. So you guys know the derivative of this. The velocity would be 0 minus 9.8t. And then we're simply going to put 1 in and 2 in into that equation. And see, there's our equation at negative 9.8t. And if we put 1 in there, we're going to get negative 9.8 meters per second. And if we put 2 in, we're going to do 19.6. Okay, how long until the lolly hits the ground? How long until it hits the ground? So let's think about this for a second. So drawing a picture would be helpful. So remember, it looks something like this, where this is time, and this is 122.5 way up there. And we're trying to figure out how much time has elapsed until this happens. And so do we need to take the derivative for this? Is there anything in here that's talking about speed? This says velocity, or if it had said how fast is it traveling. This is saying how long. This is time until it hits the ground. Ground is a distance. So what we want to do is use our distance formula here, and we need to figure out which variable we know. Do we know what time is? Do we know what h is? And you guys know that we know what the height is. We know what the height is when it hits the ground. So we're simply going to set this equal to 0. And so we'll end up having 0 equals something. And then I think, have I done? Yep, I have. So I'm just going to clear the screen again. So 0 equals 122.5, and then we're really just going to rearrange this equation. So we're going to take the 4.9 to the other side, divide by both sides by 4.9, and then square root it. Obviously, this would be plus or minus mathematically, but we know with our reasoning, we understand that the negative time or negative distance is not going to make sense here. So we just report it as 5 seconds. Okay, now here's a question. How fast is the lolly falling at the exact moment it hits the ground? Well, that's classic. That's a great question. So we know that the lolly's kind of done this, and we could start asking questions like, how fast was it traveling right here, or here, or here, or here? When was it traveling fastest? That would be an interesting question. But for now, we're just wondering how fast is it falling when it hits the ground, which we then could ask questions like, at what speed would a lollipop be damaged? And so we could pick that lolly up and we know how fast it had traveled, and we know whether it could sustain that sort of velocity on impact. Okay, and since we know how long it took and we know the derivative right here, we're just going to go ahead and put that right in there. And there you go. So that is the next batch of questions there. Okay, the position of a particle moving on a line is given by the equation, this equation right here. And sometimes this picture might be better drawn like so. So just imagine you're starting somewhere and you start walking one direction and you're writing on the wall, and then you turn around and you're still writing on the wall. And then you turn around again and you're still writing on the wall. So hopefully you can appreciate that we sort of change direction in a variety of places. That's what this guy here represents. So that was a change of direction, and that's a change of direction. And how fast is it moving right there at that change of direction at that instant? Well, that's what we're going to kind of be thinking about. Okay, state the particle's position after 3 seconds. Okay, so the position here, of course, is asking for position. That's a key word. So this is a position time graph. So where is the thing in relation to time? So we're going to simply put 3 in there. And when we do that, we'll put 3 in for t and calculate, and we're going to get 45. Okay, let me just, okay. What is the velocity after 3 seconds? So in order to answer that question, of course, I'm going to need to take the derivative, and I didn't, so I'll just, the derivative is going to be the change in distance over the change in time, and that's going to equal 6t squared minus 42t plus 60. Okay, and then I'm going to put 3 in all those spots where I see the t, and when you do that, you're going to get negative 12 meters per second, which basically means that it's moving downward or back toward the direction that it started. Okay, so its distance is decreasing is basically what that means. So there'd be sort of a negative velocity in this region here, because we can see that the slope is negative. It's coming back toward it is, or in this case here, the negative velocity would be right in there as it's, we're expanding and then we're coming back to where we started from. When is the particle at rest? That's a really good question, and that's one that is going to be a classic question that you want to get used to in both this chapter and the one that follows. And so what we're going to do is we're just going to figure out when is the slope here at rest? When is it basically not moving? So in order to do that, we want to set the derivative to 0. So we're going to have 0 equals, and then I'm going to factor that 6, and it's going to be t squared minus 7t plus 10. And in this case here, I can easily factor that. So that's going to be t minus 5 seconds and t minus 2. So that would mean that the velocity would be 0 if I were to graph this at 5 seconds and at 2 seconds. Or so in case of this drawing here, right here, we turned around at this is harder to visualize, so I don't like this graph for explaining because this is 2 seconds and this is 5, so it doesn't work horizontally on that image. But if we considered this graph, which would be easier for us to make sense of that, it would. Maybe another way of seeing it is, yeah, we've just kind of changed that up. Okay, so it'd be 5 and 2 seconds. Oh, and I just explained that there. When is the particle at rest? So we just kind of walked through those steps, and there you go. The position of the particle moving on a line. Okay, so we've heard this before. When is the particle moving in a positive direction? Okay, a positive direction. When we think positive, we think of a positive slope. So this would be a positive slope up until that point, and then this would be a negative slope. We call this a negative slope, and we call this a positive slope. So essentially what we need to do is just figure out when the slope is positive and negative. If you know what the graph looks like, then it's really, really, straightforward to just look at that and know. And so we can see between 0 to 2 it's positive, and from 2 to 5 it's negative, and from 5 on it's positive. So the simplest way to do that would be to just graph it. Okay, but let's say you didn't know, you know, when it was positive and negative. One thing you could do is you could set the intervals. Okay, so I'll take you back here. So right here, we're going to have intervals between 0, 2, and 5. So if we just put that on a number line, okay, and so then all you're going to do is, if we just put hopefully you can visualize this. Okay, so the slope here, this is going off into infinity. Okay, so the slope here is either positive or negative. Okay, it's not going to change until we hit the 2, right? Like, this is when the slope is 0, and pretend we didn't know what the graph looks like. We do know that the slope is 0 there and there, and the only way you can change from positive to negative is by going through a 0. So all I'm going to do is I'm just going to test any value. So I'm going to put a 1 in there. I could choose 0.5, 0.75, 1.5. I'm going to choose the easy number 1. So when I do that, I'm going to put a 1 there and a 1 there. So this is going to be 1 minus 5 is minus 4. Okay, and 1 minus 2 is minus 1. And multiplied by 6, I'm going to get positive 24. Okay, oh, so the slope right here is positive. Okay, then what I'm going to do is I'm going to choose a number between 2 and 5. How about 3? So I'll put a 3 in there. So if I put a 3 in there and a 3 in there, I'm going to choose the pen color here. And how about, I'm not having a great luck with, okay, so if I put a 3 in there, 3 minus 5 is minus 2, and 3 minus 2 is 1. Can you see that I'm going to have 6 times negative 2 times 1, which is negative 12? Oh, the slope is negative right in here. So I can see that the slope is negative. So you could just test values, or if you know what the graph looks like, and we just know that's a positive slope and that's a negative slope, and so on. So there you go. Hope that was helpful. This next piece can be quite tricky. Find the total distance traveled by the particle during the first 6 seconds. This is the most common error in this section, total distance. Let's go back to that frog. The frog jumped up and it jumped down. What's the total distance traveled? The answer is not 0. The frog jumped up, it jumped down, it just happened to land in the exact same spot. But it moved up, it moved down. So similarly, after 6 seconds, we're right here. But the frog did, or the particle didn't just simply move that distance there. It moved all the way up to there, then it moved from there to there, and then it moved up to there. Can you see that? That's a really important observation. So most people who get this question wrong will simply put a 6 into there, which basically finds this height, but that's not the total distance. That's the position that the particle is after 6 seconds. It's not the total distance. So total distance and position are not the same thing. So how we want to go about solving this problem is, first off, figuring out how far did it travel from 0 to 2 seconds. And it looks to me like it's around 50-ish, and then that looks like about 26-ish, and then it looks to me about like 35-ish or something. Okay, but we can do a bit better than that. So here's what we could do. All we're going to do is we're going to put 2 into this equation. You get 52. We're going to put 5 into this equation. You're going to get 25. We're going to put 6 into the equation. We get 36. So the answer is not 36. That's the particle's position after 6 seconds, but that's not how far it has moved. Take this for example. Imagine the particle's doing like that. You could say that it hasn't moved at all because it's where it started. If this is time, and this side here is distance. So if this is distance and this is time, well, you go up and down here, the distance is still 0 again. Okay, so let's just make sure that's clear. So can you see that it went from 0 to a height of 52, and then it went from a height of 52 to 25, and then it went from 25 to 36. So if we take these numbers and go 52 minus 25, you get 27. This is a bit. Sorry. Excuse me. We went from 0 to 52 first. Obviously 52. Then we went from 52 to 25, which is 27, and then we went from 25 to 36, which is 36 minus 25, which is 11. You add those all up, you get 11. Now, some of you may have noticed that we went 52 minus 25. sorry, let's try that again. We went 52 minus 0, and then we went 25 minus 52, and then we went 36 minus 25. Notice over there, I mixed the order up. So the better way of doing it would be using absolute value brackets. And basically what that does is we know that 52 minus 0 is 52. So that equals 52. And we know that 25 minus 52 is negative 27. But that doesn't make sense in terms of the total distance traveled. What does make sense is that the total distance traveled would be, oops, what happened there? I don't know what happened. Okay. What would make sense there would be that it traveled 27, a total distance of 27. Positive or negative doesn't matter. The negative here means that it's moving in a descending distance, or it's moving back closer toward, but it's still moving the distance. The energy is still being expended. And 36 minus 25, of course, is 11. And when you add all those up and take the absolute value, meaning how far away is that number from 0, we still get 90. And there you go. Okay, so I think it's time to self-assess. Can you show how derivatives are related to distance, velocity, and acceleration algebraically and graphically? And can you solve problems involving distance, velocity, and acceleration? So we'll spend more time on the graphical concept, but you should be able to talk about the velocity being the first derivative, or dh dt, and you should also, we've just played around with some problems where you're playing around with those things. Okay, so there you go, friends. Hope that was helpful, and we'll see you soon.